So moving further, this is the next lecture. What we have seen so far is we have seen a series of lecture. We started with the active elements and the passive elements. The active elements, which are the current sources, and the passive elements like the resistors. Again, we saw the KVL and the KCL, which are the voltage and the current equation of Kirchhoff's, which are one of the two most important equations. Then the last lecture what we saw was we saw the loop analysis, or what we saw was the loop analysis or the mesh analysis for the solution of the equations, the solution of the circuits. uh, so these are the two things which we saw. So again, coming to the one more way after the loop or the mesh method to solve the circuit is the node analysis. So coming briefly, making a point here is that it's possible to solve the same circuit by same circuit by using mesh analysis. Also, sometimes it's possible to solve the same circuit by using the node analysis. The choice depends on the method which you are more familiar, or the method which is asked in the question, or the method which can provide the solution more quickly. So in the node is a point in a circuit where two or more passive or active elements, where minimum two passive and active elements are meeting. It can be two passive elements, or it can be either one passive element and one active element, as in this case where the voltage source is one element and the current is one element. They are meeting so at a point, so this you can call as a node. So this is one node. Again here, this is another node where three passive elements are meeting. So this is one more node, and again this is one more node where one passive element, this is a passive active element, and one passive element are meeting. So, and you will need one more node which is known as a common node, and this node is usually connected to the ground or the earthing, and all the nodes are having a common node. So this is a usual circuit, and this can be solved using the node method. So we will use this circuit in this example by applying the node voltage method. The first step in node voltage method is identifying all the nodes. So you have identified three nodes possible in this circuit, 1, 2 and 3, and then there is a fourth node which is always to be taken, or one common node is always to be taken, which is the fourth node in this case. And by using the nodal analysis method, we can find what we are going to find here is we are going to find the current I1 and current I2 and I3. So by using this method, in the circuit, we will find the current I1, I2 and I3, just to demonstrate how you can use this. So the current I1 can be written as VA minus V2 divided by R1. That is a no, that is VA is voltage at this node. So VA minus V2 divided by R1, that is a voltage drop across this resistance. So seeing further, so that current I1 can be written using by after identifying the nodes and the node voltage as this way. The current I2 can be written as this way, R1 is, and current I3 can be written as this way. So again, further solving by using KCL, you are applying the KCL at this node, that is a node 2. It is found that I1 is equal to I2 plus I3. So you will need minimum two equations to solve the circuit. So one kind of equations which you found was you applied found out all the nodes, and you found out all the equations for all the current using the voltage drops by considering the voltage at each of the nodes, and then you used the KCL to write down the equation as this way, applying that one node. So after substituting the values for the I1, I2 and I3, whichever you have found out, what you will find is that you can easily find the value of the voltage V2 after solution. So you have got the voltage of one of the nodes, that is node number V2. So now you can substitute that. You have already know VA, that is given as a voltage source as 10 volts. So you have found V2, you know the resistance, so you can easily find out the resistance current I1. Again the V4 will be 0, since this is a ground voltage and the ground potential is always 0. And you can find out the I2 also, since it is you know the V2. And again you can find the V3 also. So in this way you have found out the current for all these circuits. And while finding out the current uh, for the circuit I3 is 0. Why it is 0 is that uh, the current no current will flow through this, since we have found out V2 as a 10 potential, and again this is also at a 10 potential. So both of these are at the same potential, so there will be no flow of current in this loop, or in this resistor in this case. So that's how you can even validate if there is any wrong thing, or if you can revalidate the circuit also. And in our case there was no current flowing through the I3, as it is at the same potential and can be validated here. So that's how you can apply the node voltage method to solve the circuits. So again this is for DC circuits, or the circuits in which no current will be, or the DC current will be flowing. So while I will be preparing more lectures about the AC circuits, and in that we will solve the same kinds of circuits, same kind of circuits by applying the node voltage analysis. But in that case, if you are considering the AC circuits, you will also have to consider the inductance and the capacitance. That's all. If you like this video, please do watch the few more videos in this series. The next I will cover about the superposition theorem, and finally I will cover about the Thevenin's and the Norton's theorem. Then I will close the lectures about the DC theorems, and I will start about the AC networks and AC theorems.